Okay, so this goes along with chapter 13 in your book. Okay, so basically what we want to be able to do, you want to be able to identify various piping systems. We want to recognize plumbing fixture symbols on prints. Okay, you're not going to want to put your furnace where there's supposed to be a restroom or something like that. You need to know where the piping goes. You need to understand where the drains go. And that's basically because of condensate piping. Okay, as well as if you're installing a boiler in a commercial environment, you need to be able to know, like, okay, where's my closest water availability? Okay, we want to explain the 3 stages of plumbing installation, and we want to be able to sort of read a piping diagram. I just want you to be able to locate things. Okay, when we talk about a plumbing installation, stage 1 is done prior to pouring a foundation. Okay, in other words, we can't pour a foundation without having the plumbing pipes that go through the foundation in place, because it's much easier to put the pipes in before you pour the foundation and your subfloor rather than after. So what they do is they put the pipes in, they put your service entrances. By service entrances, that's your feed from the street for your clean water, okay, and your sewer drain outlet wherever it goes to the street or to septic system. Okay, that's done prior to the foundation. So trenching is done ahead of time. Stage 2, okay, it's completed prior to slab on grade constructions. In other words, the plumbing is all roughed in. What that means is the pipes are put in. Okay, things are put in their proper locations from a piping perspective, especially if it has to go under concrete subfloor, because they'll pour the concrete right over it. If it goes under subfloor, it's PVC material most often, or CPVC. You do the installation of water supply and sewage drain pipes. That's stage 2. Stage 3 is done after the walls are finished. We finish the plumbing, we install the fixtures, we install the appliances. So plumbers are basically there in 3 stages of a larger project. Okay, they're there at the start before anything is even there, where there's plain ground. They do their trenching. Stage 2, they're back when the floors are being poured, when the walls are being put up. And stage 3, when everything's done, they're usually one of the last trades in. So again, this is their stage 1. The trenching is done. They have their, you can see where the foundation is going. They have their service entrances there. So everything's there from a stage 1 perspective. Stage 2, the floor isn't poured yet. They have the gravel down, they have everything down, but anything that has to go down through the floor is being connected. It's all being roughed in. All of this is going to end up being behind walls eventually, but the plumbing is usually one of the first things that goes in. And then the stage 3 is obvious. Their walls are up and everything's being finished. So a water distribution system. When we're looking at prints and see a water distribution system, it's the main supply line from a municipal meter. In other words, the town's meter or another supply source. Could be a well, could be a water tower. Okay, it's your main supply line. And it contains all the pipes that distribute water to the service outlets, like going to a water heater, to the sinks, to the restrooms, to any outside hose bibs. It includes all the control valves. Now, the best plumbing projects have a big manifold in the garage or basement or wherever your center of the point of the house is, wherever the main comes in, and every one of these different areas has its own valve, okay, and it has its own run, but that's expensive. So a lot of times they do a perimeter loop. That's basically a loop around the entire house or building, and everything comes off of that. That's a little bit less expensive. But obviously, if there's a leak in the loop someplace, you lose everything. So again, this is the distribution, okay? Now, when we look at a plan, we actually see the water distribution, okay? It's tough to see on this plan, but if you look at, you can actually see these black lines that show where the water distribution is, okay, down here near the bottom. Let me grab a pen. The heavy black line on this slide, and I know it's hard to see, Okay, there's a black line that comes through here. It's just like a ductwork line, but it's on the plumbing plan. Tells you pipe sizing, tells you where the valves are, tells you where everything goes on the plumbing side of things. Piping materials for water distribution, copper piping, okay, is used unless it goes in concrete. You cannot use copper piping if it's in concrete. Galvanized steel piping is used in some construction, less and less, because that rusts. Plastic pipe is used very often, okay? It's PVC or CPVC. CPVC is just a little bit of a different PVC material, okay? If you go through any concrete, you have to use plastic. You cannot have copper touching concrete. Okay, copper and plastics are the most common for residential installs. Quite frankly, from Virginia south, you're going to see more PVC being used than anything else. From Virginia north, you're going to see more copper being used. Okay, it's just the way they did it, but again, it's copper and plastic. Okay, tankless water heaters are being installed more and more. They produce instant hot water. They supposedly last longer and require less energy. Water's heated only as needed. If you're in a larger building, they may install more than one. Okay, they might install one special one for a master bathroom, one for the rest of the house. Okay, word of warning on tankless water heaters. If someone wants to install a hot tub or one of those Whirlpool tubs, okay, specifically like in the master bathroom where they have the 6-seater tub in the master bath, okay, you cannot do it on a tankless water heater. It doesn't have the capability to fill a large tub. Okay, it's meant for stuff like showers, sinks, dishwashing, and stuff like that. But it just doesn't work for larger water use. When we're talking copper piping, and again, we're going to talk more about this in your piping course, okay, it's available in heavy, medium, and light wall thickness. It has hard or soft tempers. Again, should not be embedded in concrete, should never come in contact with other metals. Okay, copper and other metals don't get along well together. Okay, there's a reaction that happens and it will break down the copper. Pipe joints are either sweated, which in other words means soldered, or threaded. Now, in refrigeration, we started talking a little bit about brazing. I know someone was starting to work on brazing those projects, the boards together. Okay, but when we're talking water pipe, we cannot use braze. We use solder. When we're talking refrigeration, we don't want to use solder. We want to use braze. Okay, it has to do with the pressures and has to do with it. Now, when you're using solder, you cannot use any solder that has lead in it. Okay, that's very, very critical for water piping, especially for feed water piping, the water supplies. You cannot use solder that has lead in it. So you got to be careful and make sure you read the roll of solder. Okay, threaded piping I like because it doesn't leak. Galvanized steel piping, okay, has a lot of strength and stability. Okay, it doesn't break down, but it does have a coating that's supposed to protect against rusting. Now, this works for maybe 10, 25 years, but I've started to see some of the older galvanized pipe will eventually start to rust out internally, especially if you have water that is very hard water. There's 3 grades available. You have standard weight, extra strong, and double extra strong. Standard weight is used for most residential and light commercial systems. When you start getting into sprinkler systems and fire control, you're using the double extra strong. But you're not really going to worry much about that. And I don't think you'll see a lot of galvanized steel piping out there. Plastic pipe is used extensively. Okay, this is by far the primary piping. It's cheap, it's easy to install, you don't have to solder, you prime it and glue it together. It's typically rated according to wall thickness and its ability to carry hot water. Joints may be threaded, solvent welded, in other words, that's your primer and cement, or connected using special fittings. Okay, coming down after I moved down to Florida from the Northeast, it was a real tough thing to get used to the plastic piping, the PVC. Everything down here is PVC. So it actually took a little bit of, okay, well, I'm not used to putting this stuff in. I'm not used to working with this stuff. And it was a changeover period to get used to it. So, again, the solvent welded, it's easy. It just has to be clean. The minute you get anything with plastic pipe dirty, okay, in other words, get sand or dirt on the ends or any contaminants on the end of it, it doesn't seal properly and it will leak. So that's why it's so important to get the purple primer on it. Okay, the building officials look for the purple primer. If they don't see it, they get upset. They make you redo it. So you got to prime it, you got to cement it, and it got to be done properly. And again, you will have a chance to do this in your piping class. There's different types of plastic pipe. You have PVC, used basically for cold water supply piping and sewage piping. You have CPVC, which is just a different type of PVC. It has the ability to carry hot water. That's the difference. Plain PVC won't handle hot water very well. CPVC uses hot water. Then you have PEX tubing. It's a flexible, lightweight tubing, but it needs to be supported. It sags. Honestly, if I had to repipe my house, I'm going with PEX because I can pull it through the walls just like wiring. Okay, and I don't have to, it comes in 150-foot rolls, and I don't have to make any joints between the fixture and the main water supply. PEX tubing is being used very often. And then you have ABS. ABS is the black PVC. It is strictly used for sewage piping. And it isn't used all over the country for sewage piping. You see it used in different areas. But it's the black PVC. Any questions yet on anything I've gone over? Okay. When copper pipe passes through a concrete slab or masonry wall, we run the copper pipe through a plastic sleeve. In other words, if I have a wall here, okay, I'm going to put a plastic sleeve or a PVC sleeve, and I'm going to run my copper pipe through the center of it. Okay, again, we use a larger pipe than what we need because I have to allow for expansion and contraction. We cannot have copper any time come into contact with concrete. The copper will break down, okay, and it's going to leak. Now, when you run a plastic sleeve through a wall, okay, you do have to seal around the piping on both sides. That's to prevent critters from coming in and out, okay? So you actually, what you use a lot of times is silicone or foam insulation or something like that. You need to seal these holes because that's big enough for rats and mice to run through as well as whatever all else wants to get into the building. So you need to make sure you seal around it. Okay, what's on the screen right now is a 3D look at a plumbing drawing. Okay, it's basically you're looking at this and you're seeing, okay, this is my ground floor, and then we go to my fixtures, my drains and pipes that are on the ground floor. Then we have our risers up to the next floor. Okay, we have our second floor. And then over here, we have some additional piping that comes off for something up here. These symbols right here that I just circled right now, those are valves. Okay, anytime you have that, that's a valve. Okay, this is probably a 50-gallon water heater over here. It has an inlet and outlet, valves on both sides of it. So the water heater in this building is not on the ground floor. It happens quite a lot. Questions on this drawing? Okay, Plumbing symbols. This is probably one of the most important things that I do want you to be aware of. Am I ever going to test you on it? No. But is it important to read, to understand these from reading a blueprint? Yes, and they're in there. There's a page of these in your construction blueprint book. Okay, you have differences between cold water supply, hot water supply, soft water. That's basically drinking water, treated water. Okay, now the lines are sort of important, okay, but it's, again, hot water has 2 small dashes between every long. Cold water just has 1 small dash between every long. Okay, on plumbing symbols, gas piping shows up on the plumbing plans a lot, and that's also important. Gas lines show up. Why are they important to you folks? Because that's where you have to connect furnaces and water heaters to. Okay, but the plumbers most often run the gas lines. Vent piping is just plain dash. That's the vents that go up to the roof. You can't tie into those. Soil or waste pipe, that's your sewer line. Okay, that's important because a lot of times that's where you're going to tie your condensate lines into. Okay, and all of these, it becomes important, like the valves, the motors, or meters and stuff like that. Just be aware of what these symbols are so you can sort of understand them when you're looking at a plan. You're not a plumber. We're not training you to be plumbers, but it's important to understand it as part of the blueprints. Questions on these symbols? Sewer disposal systems are also known as drain, waste, and vent systems. Okay, DWV, our plumbing program has 2 entire courses on this, DWV1, DWV2. Okay, it includes a vertical stack, has a vent, has a trap for each fixture, and has a clean out of each, at the base of each stack. The stack is basically the line that runs from the top of the house to the bottom of the house, from the highest level to the lowest. Vents go out through the roof. They allow the air pressure to help with the drainage. Okay, it pushes the sewer through and it allows the escape of sewer gases. Plumbing codes start with the Uniform Plumbing Code, International Plumbing Code. In the United States, in most states, we use the International Plumbing Code as our base for plumbing. Okay, different states may alter that. They can add to it, but they can never subtract through it. Okay, code provision includes the kinds and sizes of pipes to be used, location and traps and cleanouts, fixture requirements, in other words, how many gallons per minute am I allowed to have in a toilet? Okay, I mean, again, it's water-saving devices. Venting provisions, how many stacks do I have to have going through the roof to allow escape of sewer gases? Tells you how you can connect them to the supply and sewer lines. And it tells you how you can leak test. Everything that has to be, everything that we install that carries something, fluid, gas, anything, has to be leak tested. And the building officials want to see those leak tests. In other words, you can't just install a gas line and say, okay, yeah, it's not going to leak because I did it. You have to prove it. Now, all of this here, the connections are all done by a plumber. Everything up from this point is normally the responsibility of the plumber. Anything you install, anything you add, like a gas line, like a condensate line, that is your responsibility. Okay, that's where the line is drawn. The main systems are done by the plumber. Anything you tie in after the main system is complete becomes your responsibility. Okay, and yes, you do have to pull permits on a lot of this stuff, and yes, they might have you say, okay, we need a plumber, a licensed plumber to sign off on this. Okay, every state is a little bit different on what they will allow you to do and what they will not allow you to do. For example, in Connecticut, my HVAC license, my S1 license, allows me to just about do anything having to do with gas and any other line after the main. Okay, my HVAC license does not allow me to connect a boiler to the water supply. There has to be a backflow device put in. That has to be put in by a licensed plumber. Once they put in the backflow, I can do anything after the backflow prevention. In Florida, I'm allowed to do my own connections. Okay, my mechanical contractor's licenses let me do that. In Massachusetts, my mechanical license does not allow me to run gas line. Gas line is the responsibility of plumbers in Massachusetts, and they're very picky about that. Okay, it also, believe it or not, does not allow me to run flue piping from gas appliances. That belongs to the plumbers. So every state is a little bit different. Where do you find the information of what the state allows? The building officials. Questions on that? Okay, and again, this is part of the chapter, okay? The mechanical trades, you're going to see the word mechanical trades. I don't really have it up here for the purpose of the job opportunities. You guys already know that. But the mechanical trades, it's anything that's part of the plumbing, electrical, and HVAC, okay, is mechanical trades. Okay, so you're going to have the different trades in at different times. You're going to see construction foremen refer to the mechanical trades. That's anything having to do with the plumbing, the electrical, and the HVAC. Okay, that takes care of basically Chapter 13. Okay, my biggest thing I need you to know on Chapter 13 is I need you to understand the different symbols, because you're going to have to find those eventually. Like if you're looking for why you don't have water someplace, you need to be able to find the valves. Any questions on the material in Chapter 13 before we move on to heat loads? Okay, let me move on to heat loads. That's where we're going next, and that's actually the best part of the course, so let's move on to that. Okay. I will post later. I'll post the handout for the material we covered in the day, so I'll post the handouts after that. This is a very long PowerPoint series. I really just want to take it through. We'll see where we get to, and then I'll post the material from that. But one of the first things we have to understand is how building heat transfers, okay? And it's very important you ask questions as we go on through this, okay? No question is not a good question. So we want to understand why building heat transfers. We want to understand why people feel hot, cold. And I mean, for some of you may say this is basic information, but we need to get everyone on the same page before we can talk about specifics about heat transfer. So the purpose of a heating system is to bring the controlled environment to the set point and replace heat lost, okay? We have to bring it up. Let's say your thermostat's set at 72 degrees. Okay, that's easy. I can add enough heat to give you to 72 degrees. What's not easy is the fact that I have to replace that heat, the heat that's going out through the building walls. So I not only need to heat the interior space, I need to understand the heat that's going through the walls and windows and everything else like that. So that's why our furnaces have to be sized very specifically to the building it's in. Heat loss is caused by a temperature difference, okay? If my outside is cold and my inside is warm, I obviously have a temperature difference. Now, I talk about it on a future slide, but my heat loss grows with the temperature difference, okay? So if I have a 20-degree temperature difference between indoor and outside, I might have a certain amount of heat loss. If I suddenly raise that temperature difference to 50 degrees between the inside and outside, that heat loss is going to get bigger. Okay, heat always flows from warmer to cooler. So temperature difference makes a big difference. So what is heat loss? What causes heat loss? How's heat loss measured? And what affects the rate of heat loss? This all comes into understanding how we size equipment. We have two types of heat loss in buildings. We have transmission losses and we have infiltration losses. When we look at your blueprints and your heat project you're going to be doing, we're going to account for two. Okay, transmission and infiltration, two different things. Transmission goes through walls. glass, ceiling, floors, and other surfaces. Okay, transmission is what, if I feel a wall and it's cold, that's a transmission heat loss issue. Okay, so transmission loss goes through walls, floors, ceilings, other surfaces. If you stand in front of a window and it feels cold, okay, just cold, no breeze, just cold, that's a transmission heat loss. Infiltration loss is the energy required to warm outdoor air leaking through cracks and crevices around the door or windows, or through open doors and windows, and through what we call porous building materials. We don't have many of those. But, okay, so if you feel a breeze that's cold, that's infiltration. Now, some infiltration is good infiltration. Some infiltration is not good infiltration. So transmission loss is one of the things we have to totally understand. Okay, why do you wear a coat, do whatever, long pants in winter, or shorts and sandals in the summer? It's because your body is going to lose heat. Your body creates heat. Okay, it's just known. Where does it go? How much does it create? It all depends on the activity. Okay, so this is also why we take activity into account when we do commercial buildings. An office worker is estimated to give off about 500 BTUs per hour. So if I have 10 people in a room together without proper ventilation, I have 5,000 BTUs per hour. Okay? That's starting to get up a lot. You put 20 people in a room together, we're starting to get close to a ton of cooling or a ton of heating, depending on how you look at it. So again, the office worker, 500 BTUs per hour. You resting on a couch, okay, without doing any activity whatsoever, produces the same heat as a 100-watt light bulb. Okay, so a resting body produces less heat. Okay, where does the heat go? To cooler places than your body. Heat will always leave your body from your warmer body to a cooler area. Now in the summer that's reversed. Your body will absorb heat. Okay, but it's not always desirable. Okay, so the heat leaves your body at a rate that's relative to the temperature difference between your body and the surrounding environment. Okay, so if you're outside in the winter, okay, with no protection whatsoever, it's negative 10 degrees around you, any heat your body is transferred immediately to the surrounding cold environment. Okay, I put a box around you, just a cardboard box, basically no insulation. It provides some insulation, but not really all that much. Okay, so my outside air might be 10 degrees. The space around my body might be 0 degrees, but you're still losing heat. You're just not losing it as much. Okay, so again, I'm losing heat. Now I add a heat source to my cardboard box. Okay, maybe a fire or an electric heater. Okay, I still have 10 degrees outside air. Cool, I'm bringing it up a little bit more inside here, but my body's still like 98, 96, 97, 98 degrees after I'm losing my heat. It's still warmer. Temperature starts to go up. Well, okay, it's still going to flow out through that bad insulation into the outdoor area. Okay, but because now I have a larger temperature difference, it's going to flow out at a faster rate. Okay, bigger fire, indoor environment, 70 degrees, outdoor environment. Okay, but again, now I'm sending heat out through the walls of my cardboard box or now through whatever I'm in, but it's still going out at a faster rate, but my fire's bigger so I can overcome it. So again, when we're looking at heat loads and heat gain, we have to make sure that our heat source is large enough to overcome whatever lack of insulation there is. Now there's another way to deal with this also. Okay, is you can put a better insulation in. Okay, you build a double-walled cardboard box with insulation. I can keep my heat source small, and I can use a combination of insulating materials and heat sources, and we can achieve a desired temperature. Okay, the thicker the wall slows down the heat transfer. That's what we're looking at when we're looking at load sizing. Okay, we look at the thickness of the walls, we look at how fast the heat flows through from the indoor to the outdoor, and we look at the size of the equipment. So that's what we're taking a look at when we're looking at load sizing. Any questions on that? Okay, so again, nature hates a temperature imbalance. There's an example given here that basically set a cup of hot coffee or whatever on a desk in a comfortable room. Come back in a few hours. Is it still hot? Nope. Why not? Because again, nature does not like a temperature imbalance. That heat is going to leave the coffee until the coffee and the room are on the same temperature. The heat has migrated out of the material. Okay, set of example 2 is the glass of ice water. I've referred to this a lot. You set a glass of ice water on a counter in a comfortable room. Come back in a few hours. Is it as cold as you left? Nope. What happened to the cold? It went into the heat because again, the heat from the room will migrate to the colder environment. Heat always migrates from periods of higher heat to lower heat. Okay, heat will always migrate from hot to cold. As the temperature of the contents get closer to the room temperature, the heat transfer rate slows down. The rate of transfer from a hot to cold environment is relevant to the temperature difference. Okay, so we have to remember 4 things. Hot goes to cold. Always. Okay, heat will always go to cold. Hot goes to cold at a rate relevant to the temperature difference between the two. Okay, at a rate relevant. So if I have an indoor environment that's 70 degrees, and if I have an outdoor environment that's 70 degrees, there's no temperature difference. Okay, so heat is not going to migrate. It's 2 environments at the same temperature. If I suddenly drop the outdoor environment to 35 degrees and my indoor is, I'm going to have a slope here and the heat is going to transfer from the hot to cold environment. Now if I drop that even further, it's going to move faster. Okay, so again, hot goes to cold at a rate relative to the temperature difference between the 2 spaces. Is there any questions on that? That's a pretty important concept. Radiant heat goes an infinite number of directions from the source, and I'll give you an example of this in a minute. Radiant heat, that's like the heat from the sun. It goes an infinite number of directions from the source, but it always goes in a straight line. Okay, it will follow the line of least resistance. So if this is the sun, okay, radiant heat will always go in infinite directions, doesn't matter what directions it goes, and it will go straight lines until it bounces into something that reflects it. So up here, this might be a wall or something. There's going to be a little bit of heat that migrates through the wall, but the majority of it is going to bounce off and go back into the atmosphere. Or if it's inside the house, it will bounce off and go back into the house. So again, heat is lazy, straight lines. Okay, it doesn't completely reflect from the insulation, but some will penetrate. So some is reflected. Goes an infinite number of directions, unless, of course, like, for example, if you have a radiant heater, okay, you have a radiant heater, there might be a shield that goes around it that causes this heat to bounce back and go into the directions you want it. Where do you see radiant heaters? Go into any home improvement store like Home Depot, Lowe's, or any of those stores, and you'll look up over the checkouts. There's radiant heaters. It warms the cashiers, but doesn't warm the whole area around it. Okay, radiant heat. Heat is lazy. It follows the lines of least resistance, as I just showed you. Okay, so we have to remember, least resistance. So if I create resistance in my walls by using insulation, heat does not penetrate the walls. So we have 3 methods of heat transfer. By the way, any of you taking state licensing exams, going for certifications or anything like that, you do need to know these. Okay, methods of heat transfer. We have conduction, we have convection, and we have radiation. And when we come to our air conditioning courses, you're going to hear me talk about this again. We have conduction, we have convection, and we have radiation. All of those methods of heat transfer is part of our building and design portion. Okay, we have to understand how these heat flows before we can design our heating systems. Conduction is the easiest one to start with. Heat transfers through a solid material. Okay, in this case, the bottom of the pan is solid. Okay, the heat from the fire in contact with the bottom of the pan transfers through to the water. Okay, so the flame is on the bottom side of the pot. Okay, so again, heat will transfer through a solid material. Okay, and again, we have a solid material, heat transfers from particle to particle. Now, when we're talking conduction, there's a term that we have to understand. It's called thermal conductivity. Okay, and we're going to use this when we start talking about how fast heat transfers through the walls of your building. Okay, thermal conductivity, it's known as K. When you look at heat loads, it's known as K. Okay, it's how well a material transfers heat. It actually applies also to, something as a U factor. If you've read your textbook chapters, you've probably seen the U chapter referred to. Okay, it's how well a material transfers heat. The higher the conductivity, the faster heat transfers. So the larger the number, the faster the material transfers heat. So when we're talking about a cooking appliance or cooking pan, we want something that transfers heat very well. When we're talking about insulation, we want something that transfers heat very poorly. So our insulations are always going to have lower thermal conductivity numbers than a fry pan. Okay? Copper has a very high thermal conductivity. It transfers heat very well. Glass and fiberglass has very low thermal conductivity numbers. Doesn't transfer heat all that well. Okay. Conduction is inversely proportional to the thickness of the material. Okay, double the thickness of a material while maintaining the temperature difference between its size, the rate of the heat transfer will be cut in half. Okay, so if I have a wall, if I have a 2x4 wall, with insulation in it, I have one amount of heat transfer. That heat transfers through the wall. If I take and I double that wall thickness, my heat transfer is going to slowly get cut in half because I now have double the material in there. Okay, so again, double the thickness of the material while maintaining the temperature difference on both sides, the heat transfer through the material would be cut in half. Okay, that's why a lot of construction has gone to 2x6 or even 2x8 on outside walls. Used to all be 2x4. But again, we double the size of the wall. The heat transfer is cut way down. Okay, in buildings, conduction occurs easily through the building materials such as glass, metal, and concrete. Okay, everything on an outside wall allows heat transfer. Glass is your biggest source of heat transfer unless specific glass is used. Poor conducting materials are usually used in insulating, like fiberglass, insulating foams, mineral wool. They're very poor conducting materials. Okay, that's why we use it for insulation. The ability of a material to conduct heat is measured in the property thermal conductivity. Okay, you divide that value by the thickness of the material measured in inches. and it yields another important term called the coefficient of heat transfer. And this is where we start talking about some of what you're going to be doing on your design. Okay, we are going to use the U factor for everything. Okay, I'm not going to have you do I'm not going to have you find the K factor. You probably won't use that at all. I'll give you tables for that. But we use the U factor. Okay, it's the coefficient of heat transfer. Again, you won't have to calculate that because I'll give you tables that does that, but you have to understand what it is. Okay, so a normal sequence to solving conduction problems, we look up the R values for the materials in a building cross-section. We add those values up and then to take the reciprocal to get the U value. What I'm basically saying is U equals 1 divided by the R. Okay, now R values are found listed on all insulation. You find them listed on windows. Okay, R values is what you're given, like R13, R14, R22. Okay, so insulation and everything has R values listed on it. But we need the U factor. U is 1 divided by R, which is the reciprocal. Anytime you see the reciprocal, it's 1 over something. Okay? So this will become a decimal place. It's much easier to work with decimal places than fractions. Any questions on that? And again, we'll work with this as you're going through your building project. Conduction can happen in fluids as well as solids. Okay? So again, conduction can happen in fluids as well as solids. Metals tend to feel cold. They may not be cold. They only feel colder because they conduct heat away from your hand to an object colder than your hand. That's because, like, you put your hand on a metal wall or the side of a metal building, it will feel cold only because it's conducting heat away from your hand. You can do the same thing sometimes with a wall with poor insulation. That wall is going to feel cold. Now, convection is the next sort of heat source. Okay? It's the transfer of heat by the movement of fluid. Okay, now, I want you to be very aware, and again, we talk about this in air conditioning. The word fluid is the official designation. But in the case of air conditioning and heating, a lot of times we substitute fluid with the word air. Okay, because air is also used for convection. Okay, so again, thermal convection, transfer of heat by the movement of fluid, is the official designation. But again, we can substitute fluid with air. For heat to be considered convection, fluid in contact with the surface must be in motion. If not, the mode of heat transfer is conduction. In other words, it has to be moving. So when we heat or cool a house, we are doing it by convection. Okay, that's a very important thing. Okay, convection. So convective heat transfer occurs when fluids at different temperatures move around within a space. Okay, and I'm hoping that I'm not dating myself and making myself too old here. This is the old lava lamps. Okay, the fluids in the different spaces have a different level of heat. Okay, and they'll conduct heat, or they'll absorb heat at different levels. Where that fluid is moving around, and it's going to cause the blobs of the lava lamp to go up and down. Okay, conductive heat transfer occurs when fluids at different temperatures move around within a space. Okay, what's the example of convection in this graphic? Okay, although the pot heat transfers through the metal of the pot by conduction, okay, the molecules of the pot are in direct contact with one another, the movement of the water is convection. Okay, the hotter water will come up to the top. It's going to cool off as it boils. It's going to sink back down. So again, that's natural convection. There's another term we have to be aware of. It's called forced convection. A fan that cools a computer circuit board is forced convection. Natural convection, cool air coming into a warm room. Again, we have air patterns. It's either forced or natural. Okay. Convection is the transfer of heat energy in a gas or liquid by the movement of currents. The heat moves with the fluid. Convective heat transfer occurs when fluids at different temperatures move around within a space. Again, let's just remember, convection is how we heat and cool rooms using forced air or hot water. Okay? And again, we have free or natural convection, we have forced or mechanical convection. Very rarely do we use natural convection as HVAC techs. Most of everything we do is forced or mechanical convection, okay, on an interior space. Okay, so that's very important, okay. Free or natural convection uses what we call the stack effect, the natural buoyancy of fluid to drive the convective flow. Wintertime, cold air falls down windows, creating drafts. Hot air rises. Okay, so again, we create patterns within a room using natural convection. Everything we do, we want to counter that natural convection. Okay, we use forced or mechanical convection. We use fans or pumps to force the flow of a heated fluid or gas. An example of this, easy example, ceiling fan. Okay, in the winter months, that hot air tends to rise to the ceilings. Okay, we want to push that hot air back down to the living zone. Okay, because we live near the floor, not near the ceilings. So again, forced convection, we're reversing the flow of nature by using mechanical convection. Very important. Warm air rises due to heat rising from the earth. As the warm air rises, cool air comes in from the sides to take its place. Okay, it's a setup of circulating airflow. Convective heat transfer occurs when the fluids at different temperatures move around within a space. Okay, and again, power plants, you can see the smoke rising, the steam rising. Okay, that's natural convection. The buoyancy of the fluid or gas to drive the convective flow. Hot air rises. Forced convection. Okay, depends on a pump or fan to force the heated fluid or gas. Forced convection. Okay, and I've already said that. Okay, radiation is the last type of heat transfer we want to talk about. Okay, radiation, electromagnetic energy is radiation. Okay, radiant energy is emitted by all matter whose temperature is greater than absolute zero. The warmer the radiant object, the shorter the frequency. Okay, types of electromagnetic waves include electric currents, heat, radio waves, microwaves, infrared radiation, visible light, and ultraviolet radiation. Then you can get into things like X-rays and cosmic rays. We're not worried about that. I'm very specifically worried about electromagnetic energy and heat. Okay, it does not need material to transfer heat from one to another. Okay, it doesn't need water, doesn't need air patterns, doesn't need direct contact. You're sitting around a campfire, you feel the heat of the fire. That's radiation. It travels outward from its source in straight lines. Okay, radiant heat does not bend around corners. In other words, if I get up and move away from the fire and go behind a tree, okay, or go behind some bushes or a car or something like that, I can no longer feel the heat from the fire. Okay, because it's radiant energy, doesn't go through solid objects. Cannot bend around corners, but it can be reflected. I can use mirrors, I can use wall material to reflect that heat. A surface emits thermal radiation to any cooler surface within sight of it. Okay? And again, depending on what the source is, you can either feel it or not. But a surface emits thermal radiation to any cooler surface within sight of it. Okay, so which of the three methods of heat transfer does solar energy use to get to Earth? It's radiation. Okay, so anybody, what's the method of heat transfer? How's the heat getting from the radiator to the cat?
Convection.
Two of you said it at the same time.
Convection.
Well, is the cat in direct contact with the heat source?
So conduction.
Okay. Now, there are three methods that are here, but directly from the radiator to the cat, that's conduction. What about from the radiator to the air around the radiator? What's that?
Convection.
That's convection. Okay, and then again, we also have radiation. That's hard to show on a picture, but it's basically the line of sight. Any cooler object, like maybe the wall behind the radiator. It's not touching, but there is a little bit of radiation going on there. What about this? Where is conduction happening?
Coffee to the spoon.
Coffee to the spoon. What about the coffee to the cup?
That
okay,
too.
what about convection? Where's convection happening? Anybody?
To the air.
Liquid to the air, yep. And radiation, there's very little, okay? I mean, I'm not even going to worry about that. Okay. I'll say this one because this is probably doesn't make all that much sense on this picture. Conduction is happening from the ball to the ground because the black ball in sunlight has a little bit of heat. Convection is happening from the air to the ball, and radiation is happening from the sunlight to the ball. Again, I'm not worried about this one. It doesn't all that show that well. Now, what about a campfire? Where's conduction happening?
Is it the wind blowing to the fire?
That's the convection, the fire to the air. Okay, that is the convection part of it.
Fire
what
to the
about
ground.
conduction? Where's the conduction happening?
Fire to the ground.
Yep, wood to wood and ground, fire to the wood. Now, what about radiation?
That goes to the skin.
Yep,
From
basically
the
fire to the legs, to the person's legs, fire to the surrounding rocks and legs. Okay? So radiation, it's not touching it, but it's straight line of sight. You might as well also say radiation is happening from the, well, I don't know, maybe the hot dog could either be radiation or convection. Okay, I'm not going to worry about this one. We've already talked about that. Okay, let's now, okay. So when we're baking brownies in a glass pan, which two methods are we using? If you're baking something, which two methods are we using?
Would it be radiation?
Convection and radiation.
Conduction
Yeah, convection and radiation. You're right. What about heat in the room moves with the warm currents from the warmer areas to cooler areas?
Is that conduction?
Convection.
Convection, it's warm currents. Conduction would be if the heat is going through the wall to the cooler outdoor areas. That would be conduction. But the warm, air, the heat moves in within the warm. It's currents. Your key word here is currents. What about you feel the heat of a wood stove when you stand next to it?
That be radiation?
Say that again. There was some background noise.
Would that be the radiation?
Okay, it's radiation and convection.
Okay.
Because you have the air patterns moving the heat, but also the radiation. In other words, the direct rays. What about warm water rises in a lake? Cold water descends. Could be a swimming pool as well.
Convection.
That is absolutely convection. You're right. Okay, thermometer under your tongue showing fever.
Radiation.
Conducting.
Conduction.
Conduction.
Conduction, there's a direct contact. Sun transfers. Sun transfers its heat.
Radiation.
That's radiation. A couple more. Just let's make sure we got this. It's pretty important. On a cloudless night, the heat escapes from our planet. It goes into space. This one's a tricky one.
I'm going to say convection.
I'm thinking convection, too.
How about radiation?
Radiation, yeah.
Because space is an absolute zero, right?
Okay.
It's always going from it doesn't matter what direction it goes. There's no insulating material. Okay, yeah, that's a tricky one. Okay, place a spoon. We talked about this over time. The spoon in the cup of hot cocoa or whatever.
Conduction.
Conduction. Okay. Now, what is measured with a thermometer?
Temperature.
Temperature. Okay. Thermos bottle has a shiny interior. What type of heat transfer does it prevent? Shiny metal prevents what?
Radiation.
That's correct. Okay, that's what I was talking about, using metals or anything that reflects the heat. Prevents radiation. Okay, so moving on, we have to talk about how heat loss is measured. Okay, BTUs per hour. Very important. Okay, this is exactly what we're doing all of our load sizing for. We're talking about BTUs per hour. How fast are we losing heat? Now, the definition of a BTU, and I know you've probably heard this before and you're going to hear it again, it's the amount of heat required to raise or lower the temperature of 1 pound of water, okay, by 1 degree. Do not get confused when you take a licensing or certification exam. They have a tendency to, on multiple choice questions, throw the 1 gallon of water. Okay, it's actually 1 pound of water. Very important. Everything is done with pounds with BTU calculations. Okay, so the amount of heat required to raise or lower the temperature of 1 pound of water by 1 degree Fahrenheit is 1 BTU. Okay, for those who actually still have them or even are able to buy them lately, the old wooden kitchen matches. Okay, the wooden stick matches that everyone used to have laying around, but we don't anymore. Okay, they actually have about 1 BTU of energy in them by the time they burn. Okay, so what we start with is now we have to take a look at the building envelope. Okay, by what I mean by building envelope, it's the area around, it's your outside walls, it's your ceilings that separate the house from the attic. Okay, that is what we're looking at for all of our heat loss calculations. We're looking at the building envelope. Okay, UAT method is how we do build heat load, and I'll explain this. We have the U value. We have the area. We have the delta T. Delta T is just the temperature difference. Anytime you see the delta T, it's a temperature difference. So the UAT method of heat transfer is what we basically use. Okay, the total area of the exposed surface is the area. Okay, that's your A, that's your area. The U value, that is something that we use tables and charts to calculate. That's the thermal conductivity of like the wall or window. And then we have to know the temperature difference. Okay, the building envelope is the parts of the building which separate the inside environment from the outside environment. Okay, so when we go back and look at my cheesy drawing that I had up earlier, and I'm great at those, let's see if I can pull that back up, okay, I am specifically talking, okay, about my outside walls. Okay, I am not talking about inside walls. I could care less. There's no difference in temperatures here if everything's right. I'm talking about my outside walls. Now, there's one area of any house to be worried about. Okay, if this is a garage, okay, and if I do not heat or cool my garage, these walls right there are insulated. They're considered outside walls. So what we're worried about is the value, the heat transfer through any wall that is not abutting heated or cooled space. Is there any questions on that? Okay, so again, the parts of the building which separate the inside environment from the outside environment. Okay, so I'm talking about the ceiling there. I'm talking about the outside walls. I'm talking about the floors if you don't have a basement. That's the slab. I'm talking about any walls. I'm talking windows. I'm talking anything like that. Okay? The attic is considered an unconditioned space, so I'm not worried about heating or cooling that. So again, I'm worried about the parts of the building which separate the inside environment from the outside environment. So ASHRAE, which is the Engineers Association, they have way too much time on their hands. They have a definition for this, of course, because they have a definition for everything. The building envelope is the outer elements of a building. It includes the walls, the windows, the doors, the roofs, and the floor, including those in contact with the earth. If you've ever lived in, or if you live in a house that is slab on grade, in other words, don't have a basement, or you go down to your basement and walk on the basement floor, those floors feel cold because the heat will go through those floors. So again, building envelope, anything that touches anything in the outside environment. In other words, unconditioned space. Okay, the building thermal envelope, okay, is also defined. Elements of a building which enclose the space, which control or regulate heat, mass air transfer like air, water vapor, and moisture between interior spaces of insulated floors, walls, windows and ceilings generally comprise the thermal envelope. Okay, in other words, your thermal envelope is everything that combines the conditioned space. Okay, it contains it. Now, do I need you to absolutely know those definitions? No, but I want you to understand what the thermal envelope is, and I want you to understand what the building envelope is. Okay? So an envelope is the skin of the building, the shell, and the enclosure. Building assemblies are any part of the building enclosure that has a boundary condition at the interior and exterior of the building. Okay, in other words, a building assembly is what's in the wall or in the window. It's what puts it all together. Okay, such as a wall assembly or a window assembly or a roof assembly. Okay, in other words, when I'm looking at the house, I just see a wall. But we need to know what is in that wall. I have the exterior brick. I have insulation or an air gap, which, by the way, is a great insulator, air. I have my interior insulation or block, and then I might have a layer of sheetrock over it. So I have multiple layers to that wall that all come together and provide thermal conductivity or lack of, or insulation. Okay? So it might be the sashes, the frame, the reveal, the brick arch, the wooden, and so on and so forth. Okay, so there's a lot in there that is part of the building assembly. Now, when we look at a wall, okay, primarily what I'm looking at is what's on the outside, what my insulation is, and then what's on my inside. Okay, I'm not going to take, I have enough leeway in my numbers where I'm not going to look at the different types of cements and stuff like that. I want to know what's outside, I want to know what my insulation is, and I want to know what's on my inside. So in other words, I want to know what the major layers are. Same with the roof. I want to know the color and type of roof, but I don't need to know, well, I do need to know the width of the plywood under it, but if there's like an additional membrane or something like that, I could care less about that. I'm caring about the thickness of the different materials, the major materials. So building component is any element or material within the building assembly, like insulation, spray foam insulation, the wood studs over here. I worry about them. I need to know the thickness and what they're made of. Okay, I need to know if they're metal or wood, because metal conducts heat faster than wood does. It makes a big difference. Okay, so someone whoever this Mr. Waggy guy down here, what a funny name, okay, has basically said if your building enclosure doesn't work, your HVAC system's not going to work as designed, even if you're fine-tuning it until you're blue in the face. And that is such a true statement. That's why I've sort of left it on slides, because it is true. You as an HVAC technician can come out and keep repairing a furnace, okay, and the furnace may not be the problem. It might be the building. Okay, and that's going to happen to you when you get in the field. That is 100% going to happen to you. You're going to get on a service call sooner or later that you're like the 7th company out there. They're going through the yellow pages, finding people they haven't called before. And it's not because they're trying to be a pain in the rear end. It's because they're trying to get their system fixed. You might go in there, see the system's working properly. You may be sorely tempted to make a small adjustment to say, okay, yeah, I adjusted it, let's see what happens. Well, then they're going to go look for the next company, because the problem might not be the equipment, and you might have to look at the house, do a quick heat load, which is why we're going through this, why this is so important, and say, it's not the building, or it's not the equipment, it's the building. Okay, it's happened. I've seen it happen. So the biggest function of a building envelope is to control the heat flow. That's your most important function of a building envelope. We also have to be able to control airflow. We will need to make sure wind doesn't blow directly through it. Then we need to control water vapor. Okay, I don't want everything getting wet inside. I don't want water vapor, humidity to be coming through. And we want to control rain penetration. Sort of goes the same. Rain is just heavier water vapor. And I want to control light, because light coming in from the outside, sunlight, is a source of heat. And I want to control solar and other radiation. Okay? And finally, this is not something a lot of people think about, we want to control noise. Okay, noise is an indoor air quality problem. And of course, we want to control fire. Okay, we don't want to have fire. So this is part of what our building envelope does. It helps control fire, especially in commercial buildings. Then a building envelope, the outside walls provide strength and rigidity. Okay, in other words, we don't want the wind blowing over a building. This is especially important if you're in a hurricane zone or in an area that has high wind. Okay, and it has to be durable. In other words, it shouldn't fall apart over time as much as possible, and the architects are looking for aesthetically pleasing. Okay, so again, all of these are functions of the building envelope. From my standpoint as an HVAC technician, I'm worried about heat flow, I'm worried about airflow, I'm worried about water, I'm worried about penetration, I'm really worried about solar radiation. Sometimes I'm worried about noise in a commercial building. And the rest of this, I'm not that worried about from a standpoint of an HVAC technician. So, we have two structures of identical size, but different materials. Okay, the difference between a wood frame and a concrete block, they can react quite differently to temperature variations. The lighter frame building will warm up much faster than the heavier block building, and require the addition of less energy input to the process. However, the massive structure will remain warmer after the furnace shuts off. The same is effect during the cooling season. Okay, this storage will be more evident in the calculation to cooling loads. Let me give an example of that. If I have a 2x4 wall, okay, and again, forgive my drawing, this is south. If the sun beating down on this wall, it's 2x4 construction. Sun hits it pretty much from, let's say, 1 o'clock to 4 o'clock in the afternoon. The heat's going to come through this wall relatively fast. 2x4 construction, it's not thick. Okay, but once the sun goes down, this wall is going to cool off really quickly, and eventually heat will start moving the opposite direction as the evening cools down. If I take a concrete block wall that's thick, 6 to 8 inches thick of heavy stone, the heat's going to take more time to warm up this wall before heat starts moving through. Okay, there's a delayed reaction. In other words, if the sun starts hitting the south-facing wall around 1 o'clock in the afternoon, that sun will not warm that wall enough to start heating my inside environment till maybe 3 o'clock in the afternoon. We might have 2 hours of direct sunlight before the heat starts penetrating that concrete. However, once this wall warms up, the sun goes down, I am still going to be putting off heat into this indoor environment for 2 to 3 hours after the sun moves off that area. Okay, and when we deal with cooling loads, we have to take that into account, especially with commercial buildings. Okay, now some of you, if you live in an older farmhouse or a brick building that has stone or brick around 2 sides of the house that get to direct sun, you may see this, that one side of your house may remain warm way after the sun goes down. Okay, sometimes in the winter months we can use that to our advantage, but in the summer months that becomes a problem. Any questions on this? Because this is sort of important as we're looking at heat load. Okay, I think that is where we are going to leave off today. Let me kill this recording here so that we can talk about anything on the course material we need to talk about.